Welcome to Monte Carlo Integration Part 4, Interval Estimates. We will be looking at a triple integral over a ball B of a function f of x, y, z dv, and we'll find that that is approximately equal to the mean over the set C of the function f times the characteristic function of the ball B times the volume of that cube C. We will consider the following problem. We'll use Monte Carlo integration to find a 95% confidence level interval estimate of the following integral. The triple integral over a unit ball of x squared plus 2y squared plus z dv, and we'll call this number, whatever this definite integral is, we'll call that I. B, as I mentioned, is a unit ball. That means a ball with radius 1 centered at the origin, 0, 0, 0 in rectangular coordinates. We want to illustrate a general Monte Carlo integration method that works for triple integrals over a bounded region. In our case, it'll be a ball of radius 1 centered at the origin. We will assume that we do not know how to compute the volume of the ball. Our calculation will not explicitly use knowledge of any volume formula. We're going to use a ball because it's a simple geometric object, and we do want to evaluate things exactly later on to compare with our estimations. So what we'll do is use a simple integrand so that we can later find the exact value of the integral and compare it to our Monte Carlo integration estimate. We're going to consider an equivalent problem for that integral over the ball B of x squared plus 2y squared plus z dz. What we're going to do is change this to an equivalent problem involving an integral over a cube C containing that ball B and a real valued function defined on C. It's going to be related to this integrand over here, but it'll be slightly different. So here's our picture. We have this ball, this spherical ball of radius 1 centered at the origin. We're putting a cube around that ball, so the ball is totally inside this cube. The cube in the x direction goes from -1 to 1. In the y direction also goes from -1 to 1, and in the z direction goes from -1 to 1. So the origin, which is right about here, I think you can see some x, y, and z axes here. The origin is at 0, 0, 0. So part of our plan is to generate random points in three-dimensional space that are inside that cube I discussed, the cube C, which is -1, 1, cross -1, 1, cross -1, 1, if you're looking at Cartesian products of sets. I'll simplify that to -1, 1 raised to the third power. Now, some of these points inside that cube are outside the ball, and some other points inside this cube are inside this ball. And so our integration is going to actually use all of the points that are outside it'll use all the points that are inside this cube, whether or not they are inside the ball, in order to do our interval estimation. So in order to do what we want to do, we need to define what's called the indicator function of a set B. In our particular problem, B will be that ball. The indicator function of that set B, which will denote chi sub B, this is the Greek letter chi here, chi sub B of x, y, z is equal to 1 if the point x, y, z is in B, and it's 0 otherwise. So a crucial step is to change the triple integral from an integral over the ball B to an equivalent integral over that cube C. So we're going to look at the integral of this stuff over B, where the integrand is f of x, y, z, and we're going to change it to something else. Instead of integrating over the ball B, we're going to integrate over the cube C. And our integrand in this place is going to be f of x, y, z times the characteristic function of the set B evaluated at x, y, z dv. So we're going from an integral over a ball to an integral over a cube. If we look at this integrand, remember how we define the characteristic function. Chi sub b of x, y, z is either 0 or 1, depending on whether this point x, y, z is in the ball or not. So f of x, y, z times that characteristic function at x, y, z is just going to be this f times 1, which is just f itself, if x, y, z is in B. If this point x, y, z is not in B, then we'll have this function times 0, and that will give us an integrand of 0 in that case. So let's do the following. For each k, let's let x sub 1k, x sub 2k, x sub 3k be a point, the kth randomly selected point, in fact, inside the cube C. So these will be generated using a random number generator in Python. Let's let the random variable x represent the population from which this random selection was made, the points in the cube. Now, we want them to have a uniform distribution, and the cube that we're looking at has sides of length 2. So the volume of that cube is 8. And so the density function that we're going to look at is going to have the value 1 over 8 for every point in that cube. Just to be a little bit less specific, I guess, 1/8 can be written as 1 over the volume of that cube. So now we're going to define y sub k about the same way that we did in the previous lectures. F of one of those points that was randomly selected from the cube times the characteristic function of the set B at that point divided by the probability density function at that point. And later, if we need to, we'll refer to this quotient as the function g at that point, x sub 1k, x sub 2k, x sub 3k. So here I decided to use x, y, and z's because I wanted to use x and y's for other things. So we have that. And so looking at what we have up here, y sub k in that case, if we put the whole thing together, remember that the p function here is 1 over volume of C. So this stuff right here is equal to this integrand divided by 1 over the volume of C. And so that's going to be equal to this function, which we have here, times this function, which we have here, and dividing by the reciprocal of this volume just gives us a factor of that volume. So far we have that y sub k is f of one of these xyz points times the characteristic function of the set B at that point times the volume of the cube. So now here's what we can say. This goes back maybe to lectures 1, 2, and 3. The triple integral over C of this integrand dv is the expected value of y. And by the law of large numbers, this is approximately equal to 1 over n sum k goes from 1 to n of y sub k. In this formula, the n that we have right here is just the sample size of the points that we took from that cube. Now, using this formula right here and plugging in what y sub k is, we just have 1 over n times, and then all of this stuff right here is just y sub k. So what we have then is that this integral up here, dv, is approximately equal to 1 over n of this stuff right here. This integral over here, the one that we started with actually involving b, before we put in the characteristic function, the integral over b of this stuff is basically the sample mean, approximately by the law of large numbers, the sample mean of the y sub k values. So what we have to do is to evaluate or estimate actually this integral using the Monte Carlo method. We have to pick random points from the cube and let n be fairly large so that you'll get a pretty good estimate, and just find the average of these types of values times the volume of the cube. So we have the triple integral over b of xyz dv is, by the law of large numbers for large enough n, approximately equal to 1 over n, the sum, where k goes from 1 to n, of this stuff. The function evaluated at a randomly selected point in the cube times the characteristic function of the ball at that point in the cube times the volume of that cube. So if we look at this stuff here, we can interpret it the following way. The integral that we have here is what? It's going to be the mean of this stuff. So the mean over the set C, we're integrating over C, basically approximating the integral over C when we look at this thing that looks something like a Riemann sum. The mean over the set C, that cube, of f times the characteristic function of b, and then it's multiplied by the volume of C. So to approximate this integral, we have to pick random sample of points in the cube, find out what the sample mean is for those points, and multiply it by the volume of the cube. So here's how we'll find our interval estimate for the value of that integral. To find the interval estimate for this integral, we'll first take a uniform random sample of points of this form. These are basically the x, y, and z coordinates for the kth point from this cube. Evaluate the integrand, and we'll call it f sub k for short, which will be f of this kth point randomly selected in the cube times the characteristic function of the ball evaluated at that point in the cube. And we'll evaluate this for each of the points that we have in our random sample, and we'll let f bar be the average or mean of these f sub k's. Let's let the variable stdev, more or less standard deviation, be the standard deviation of the f sub k's. And then the 100 times 1 minus alpha % confidence level interval estimate of the integral is f bar times the volume of the cube. This is our estimate for the value of the integral, plus z sub alpha over 2 times the standard deviation of these f sub k's divided by the square root of n, once again times the volume of the cube. If you want to, we could factor out this common factor in these terms of the volume of the cube. So we just calculate this, and we have our interval estimate. If we're looking for a 95% confidence level, the value of this critical z-value will be 1.96. Here's a Python program to do this Monte Carlo integration. First, we'll import the math library. From the random library, we'll import the function random, which will generate pseudo-random numbers having a uniform distribution on 0, 1. And from the statistics library, we will import stdev, which is the standard deviation function, sample standard deviation. Then here we'll define our integrand, which is basically a function times a characteristic function. So f of x, y, z will be defined the following way. If x squared plus y squared plus z squared is less than or equal to 1, in other words, if this point x, y, z is in the unit ball centered at the origin, then the value of the function will be x squared plus 2y squared plus z. Otherwise, the value of this function will be 0. Now the main program starts. The cube volume is 2 cubed, since each side of the cube has length 2. So the cube volume is 8. The sample of points we'll take inside this cube will have sample size 100,000, and we're going to make a list of values for the integrand at these 100,000 points we're randomly choosing. So here's how we choose and store those random function values. For k in the range of n, 100,000, x will be minus 1 plus 2 times random, y will be minus 1 plus 2 times random, z will be minus 1 plus 2 times random. So we're calling the random number generator 3 times here in these 3 assignment statements. Each time we should get a different value for random, and the values of x, y, and z calculated by these formulas will be numbers between minus 1 and 1. For instance, let's look at this line. If we have random equaling 0, then x will be minus 1 plus 2 times 0. That's minus 1. If random equals, on the other extreme, 1, then we'll have x is minus 1 plus 2 times 1, and that's 1. So the values of x that we get here will range somewhere between minus 1 and 1, and similarly for y and z. Once we find x, y, and z values in the cube, we'll evaluate this function, which is over here, at that point x, y, z, and we'll append it to flist. Flist initially was defined here to be an empty list. And now let's see how we can calculate the estimate of the integral. The estimate of our integral, is 1 over n times the sum of flist times the cube volume. So basically we're adding up all of the values of f that we computed. We're dividing by the total sample size, so that gives us the average value of f, and then we're multiplying it by the volume of the cube. So basically, this is the integral over the cube of these values in flist. But remember that flist involves that characteristic function already multiplied in, characteristic function of the ball B. Then stdev will just be the standard deviation of the flist times the volume, cube volume. The critical z value will be 1.96, and then we'll calculate the lower bound as the integral approximation minus that critical value times 1 over the square root times stdev, which is this here, the standard deviation of the flist values, also incorporating a factor of the cube volume. Upper bound is about the same, except we have a plus here instead of a minus. Then we'll do some printing. We'll print out just program for n equals, and then the value of n. We'll print Monte Carlo point x approximation is, and whatever the value of I is. We'll print the 95% interval estimate, and that's going to be the lower bound and the upper bound separated by commas. and we'll print out the value, exact value of the integral, and that, as we calculated before, was 4/5 times math.pi, 4/5 times pi. And we found that this was the exact volume by symbolically integrating using sage math. So what happens if we run this program twice? Let's look at the outputs. The first line came from a print statement. Program 4, sample size n is 100,000. The Monte Carlo point approximation is 2.4895. That's an estimate of the value of the integral. Using our interval estimate formula, we get the 95% confidence level interval estimate is this, and the exact integral, which we computed using sage math, involved pi. But here is that exact answer rounded off to a certain number of decimal places. And if you look at this, 2.513 is between 2.463 and 2.516. So in this case, this interval did capture the actual value of the integral. In this next example, the exact value of the integral, it didn't change, it was the same integral, so it's still 2.513 and this stuff. And our interval estimate was from 2.511 to 2.564. As we can see, this interval, once again, does capture this exact value. We would expect that if we ran the program many times, much more than just twice, in the long run, about 95% of the intervals that we compute would contain the exact value of that integral. Thank you for your time and attention in watching this video. Let me make just a few comments. The triple integral that we were looking at was not an exceedingly difficult integral to do by hand, but it would still be kind of long and onerous to do. Most likely you would have to use spherical coordinates to make the integration fairly easy. And there's lots of room to make mistakes. I think the first time I evaluated this one by hand, I scribbled on 3 pages and then had to find a mistake somewhere on those 3 pages to correct it. But these days with Sage Math, to do symbolic calculations, we can speed up the calculation, or we can use it to help us find errors in our own hand calculations. I would recommend you try doing this triple integral by hand, and maybe try using Sage Math to see how you can evaluate that triple integral as we did by iterated integrals. You might note in the program that we put all the sample values of our integrand, which I'll just call f here, into a Python list. Excuse me. And then we called a library function to calculate the sample standard deviation. So this only required a couple lines of code, actually. Well, actually more than that, because we had a loop for putting all the f values into a list. But once we had that, we just called standard deviation library function, and we were on our way to completing our calculation. Near the end, we also used Sage Math to symbolically calculate the exact value of the integral so we could compare it to our estimations. And we saw that we were getting pretty good estimations, and we were getting interval estimations, at least in the few that we showed, that actually did contain the exact value of the integral. If we use larger sample sizes, we would get shorter interval estimates, which would give us more precision in the value of the integral. I hope you enjoyed this, and hopefully see you next time.